Section 12.1 One-Way Analysis of Variance, ANOVA. For the section 8.2, we perform an hypothesis testing for the population mean. And at that time, we only have one population. So our null hypothesis is going to be mean equal to a value. And then on the section 9.2, we perform the hypothesis testing for the population mean. At that time, we do have two populations. So our null hypothesis will be comparing with the mean 1 equal to the mean 2. And for these sessions, we'll perform the hypothesis testing for the population mean, but this time we do have 3 or more populations. So you could see our null hypothesis. There will be mean 1 equal to mean 2 equal to mean 3. It depends on how many populations do you have. Definition: one-way analysis of variance, ANOVA, is a method of testing the equality of 3 or more population means by analyzing sample variance. One-way analysis of variance is used with data categorized with one factor or one treatment, which is characteristic that allows us to distinguish the different population from one another. So we do have the two-way analysis of variance. Two-way analysis means we will have the two factor or two treatments. But for this course, we only cover the one-way analysis of variance. Why ANOVA? When comparing more than two means, t-tests become inefficient and increase the type 1 error. So if we have more than two populations, if we're still using the t-test, that will be increase the type 1 error. So ANOVA provides a single test to check if group means differ significantly. And because the calculations are very complicated, and we emphasize the interpretation of the results obtained by using the technology. So before that, we're gonna introduce a new distribution. We have learned the z distribution, the t distribution, and the chi-square distribution. And for these sessions, we'll be introduced a new f distribution. The f distribution is not symmetric, it is skewed to the right. F distribution is similar to the chi-square distribution, skewed to the right, and the values of f cannot be negative, only positive numbers. The exact shape of the F distribution depends on the two different degrees of freedom. So we do have 2 degrees of freedoms. First one, degree of freedom of numerator. Okay, that will be k minus 1. And the degree of freedom of denominator, that will be k times n minus 1 here. Okay, we're gonna talk about it later on. What is your k, what is your n stand for? So one more time, f distribution skewed to the right, and f cannot be negative. We do have 2 degrees of freedom. Look at this example. We are interested in student study skills in a university. We are randomly select students from this university. We select 5 people in the first year, 5 people in the second year, and 5 people in third year. The students were given a study skills assessment, have a math score of 100. We are interested in whether or not a difference exists somewhere between the 3 different years level. We will conduct this analysis using ANOVA. So you can see we do have 3 population. Okay, year 1, first population. Year 2, second population. Year 3, this is the third populations. And for each population, we do have 5 people in here. Okay, now let's look at the notation. N represent all data sets have the same sample size. Okay, you could see population 1, 2, 3, all of them, they do have the 5 sample. So N will be equal to 5. And then number of data sets. So we do have 3 population, so the k equal to 3. Now, I want you guys try to plug in the year 1, the population 1 data to your L1. Find out what is your sample mean and the sample variance. Okay, now let's input the year 1 to my L1. Go to the stat, go to number 1 added. So 80, 90, 85, 65, 70. You could also input the data for the year 2. And then the year 3. Now, I want you guys find out each population, the sample means and the sample variance. So click on the stat, go to the cal, number 1, one variable statistic. First, I'm gonna figure out the L1. Go to calculate. So you're gonna see I do have the sample mean 78. And then sample variance, they only give you the sample standard deviation. So I'm gonna write down this number, 10.368. And then take square, that's a sample standard deviation. So take square, that will become the sample variance. So for the first set data, I do have these two numbers. So I want you guys to do the same thing. Figure out the sample mean and the sample variance for the year 2 and for year 3. Okay, do the same thing. Go to stat, cal. This time I'll do second 2 for L2. Go to calculate. So I do have 80.2 and write down this number, 15.205. Take square. Okay, that will be the sample variance. So check your work. You should have these numbers. Okay, now look at the new notation. This is called the variance of the sample means. So means like I do have the sample mean here, and I want to use these 3 numbers to find the variance. So what we're gonna do, go to the stat, add the number 1. I'll use the L4 as well. So 78, enter, 80.2, enter, 83, enter. Okay, find out the variance using these 3 data. So go to the stat, cal, number 1, one variable statistic, and then my data is going to be on L4. So second 4 for L4. Go to calculate. So write down this number, 2.50599. Take square. Okay, so you're gonna get this number, 6.28. This is called variance of the sample mean. And then one more notation, mean of the sample variance. So this is my sample variance and I want to find out the mean. So since we only have 3 numbers, so I would just add it up together and then divide it by 3, just like how you guys finding the sample mean. So add up these 3 numbers. All right, divided by 3. So you're gonna get 126.23. This is gonna be mean of the sample variance. Okay, mean of the sample variance. We just finished the calculation. Now let's talk about the ANOVA. ANOVA is talking about the total variability. Total variability, that will be equal to between group plus the within group variability. This guy, the variance of the sample means that will belongs to the between group variability. And then the mean of the sample variance, that will be represent the within group. Okay? So in this example, we do have a total variability in all 15 scores. It can be split into between group. Okay, the difference among the 3-year level means. And the within group. Within group is talking about the difference among the students within each year. So ANOVA will be compare these two sources. If between group is much larger than within group, it suggests the factor has a real effect. The comparison will be using the F distribution. This is how we find the F statistic. The F statistic will be equal to the between group, this number, divided by the within group here. Okay, so this is the test statistic. So now I'm gonna plug in the numbers. We do have an N here, gonna be 5 times the variance of the sample mean divided by the mean of the sample variance. This is how we calculate the F statistic. And that will be equal to 0.2488. This is just an example to show you guys the idea of ANOVA and the part of the calculation. Now, let's look at the step. What is the procedure to perform the one-way analysis? First, verify the condition. Populations have approximate normal distribution. So for each population, they do have a normal distribution. Second, population have the same variance. Okay, this is talking about the population's variance, or you could think about it, they do have the same population standard deviation. Number 3, simple random sample of continuous data. And independent sample. The sample should be independent for each other. And the different samples are from populations that are categorized in one way. Okay, one factor or one treatment. Now, identify the null and alternate hypothesis. So, we want to test the equality of the population mean. Okay, depends on how many populations do you have. And then alternate hypothesis, that will be at least one of the means is different from the others. The test statistic, this is the formula, but I will let you guys use the calculator. Okay, find the p-value and interpret the p-value. So this is the F distribution. Again, this is skewed to the right and is always white tail. So how to find out the degree of freedom of numerator? That would be k minus 1. K, that is represent how many populations do you have. And then degree of the denominator, that would be k times n minus 1. We assume they do have the same sample size on each population. Okay, just like our first example, n will be equal to 5. The p-value will be using the FCDF. The test statistic and upper value 1D99. And then degree of freedom of numerator and the degree of freedom of denominator. After you get the p-value, compare with your significance level. Less than or equal to, we're going to reject. Greater than, we're going to be fail to reject. And then, we're going to draw the conclusion. If you reject the null hypothesis, there is sufficient evidence to conclude that at least one group mean is significantly different from the others. If you fail to reject, there is not sufficient evidence to conclude a difference among the group means. Okay, this is the step how you guys use your calculator. Example 1. Simple random samples of 3 weights after treatments with nothing, fertilizer, irrigation, or both are listed below. The samples were independent and taken from normally distributed population with the same variance. Use the p-value method and 5% significance level to test the claim that the treatment samples come from population with the same mean weight. Okay, so we do have a 1 population, 2, 3, and 4 population. And this is just like chain number 1, chain number 2, chain number 3, and chain number 4, and chain number 5. First, let's verify the condition. Population have approximately normal distribution. Okay, so this is given. And then they do have the same variance, given. Simple random samples of continuous data. So the chi weights, this is a continuous data. And we assume this is going to be the independent samples. The different samples are from the population. They are characterized in only one way. Okay, this is a one-way ANOVA. Okay, then we try to fill in this table. Okay, so sample size, we do have a 5, right? 5 sample for each population. Sample mean, you're gonna plug into your data, find out the sample mean and the sample variance. Okay, so we're gonna input the nothing on your L1 here. So 0.24. I also input the L2. L3. And the L4 here. Okay, right? Now, I'm gonna figure out the L1, what is the mean and the sample variance. So I'm gonna go to the cal, number 1, one variable statistic. So second one for L1, calculate. So I do have a 1.19 here. Okay, for the sample variance, we're gonna use the sample standard deviation. Try to get more decimal space in here, 0.625739. And then take square. You're gonna get this sample variance, 0.39155. Okay, I want you guys to do it one by one, figure out the sample mean and the sample variance. Okay, check your work. You should have this number. Okay, now figure out the variance of the sample mean. Remember how to do it? Go to the stat, number 1 added. I'm gonna input this number on my L5. Okay, go to the stat, cal, and then my data is gonna be on L5, calculate. Okay, write down the sample standard deviation. Sample standard deviation, take square, that will be the sample variance. So that will be 0.205. Okay. Now, find out the mean of the sample variance. You could just add up these 4 numbers divided by 4. So you're gonna get this number as well. I try to take more decimal space in here though. Okay, you don't have to, you could take like 3 or 4 decimal space, that would be good enough. Okay, state the null and alternate hypothesis. We do have a full population. So the H naught, that will be mean N represent nothing. Mean fertilizer and mean irrigation, and the mean B, the both. And alternate hypothesis, that will be at least one of the means is different. Okay, test statistic. You could use this formula, okay? And then plug in N equal to 5. Plug in variance of the sample mean and the mean of the sample variance. You should get this number, 3.7046. Okay, then find the p-value and interpret the p-value. So first, we will have the skew to the right. We find the test statistic, and that will be the p-value. And area of the white tail will be equal to your p-value. Okay, now let's try to find out the degree of freedom of numerator and the degree of freedom of denominator. So k minus 1. K is talking about how many population do we have. We do have a full population. So you could get equal to 3. And then n, that will be the sample size. So that will be 5 sample size here. So 5 minus 1, 4 times 4, which is going to be equal to 16. And then we're going to find the p-value. We'll be using the FCDF. Lower value, upper value will be 1D99. And then degree of freedom of numerator, degree of freedom of denominator. Use your calculator. So go to second, vast. Going down, you're going to find the FCDF. Enter. So lower value, upper value 1E99. Degree of numerator 3, degree of denominator 16. And then paste. Okay, so you should get 0.034. And then we're going to compare with your significance level, which is going to be less than or equal to. So we reject the null hypothesis. And then now we're going to draw the conclusion. There is sufficient evidence to conclude at least one treatment samples from one populations with different mean weight. Okay, now let's use the calculator to check our work. Go to the stat, go to the test, go up, you're gonna find the ANOVA. We do have a full population, so second 1 for L1, comma, second 2 for L2, comma, second 3 for L3, comma, and then second 4 for the L4, and then enter. Okay, so first, you do have the test statistic 3.70546 or here, right? And then you have the p-value 0.0337 or 0.034. Okay, you're gonna see that as a factor, degree of freedom. This is talking about the degree of numerator. Okay, so we're gonna get the 3 here. And then going down, you're gonna find the error. This is the degree of freedom of denominator, which is gonna be 16. Okay, right? Okay, now let's look at the screen here. I just copied the picture from the calculator. Okay, this is gonna be the test statistic. And then the P here, this is represent your p-value. And then the factor, degree of freedom, this is talking about the degree of freedom of numerator. And this guy, that will be the degree of freedom of denominator. Okay, under the factor, under the error here. Okay, and then under the error, MS, this number, this is represent your variance of the sample mean. Remember on our example, for the last column, we add it up and then divide it by the number of data, mean of the sample variance. And then this guy, under the factor, the MS, this is talking about the N, sample size, times the variance of the sample mean. Okay, variance of the sample mean. So you could see, variance of the sample means equal to 1.025. And then we're going to divide it by N for both sides here. So this cancel out. The N, that will be equal to 5. So when you divide it, you're going to get 0.205. It match with here, 0.205. Right? This is going to be variance of the sample mean. Okay. And then the test statistic, you could just look at your calculator, the MS factor, which is going to be 1.025 divided by the error MS, which is going to be this number, 0.276825. You're going to get the test statistic here. Okay? Okay, now let's work on the example 2 here. The stress deceleration measurements in gram, where gram is the force of gravity, from samples of small, mid-size, and large car. Assume that we plan to use a 0.05 significance level to test the claim that the different size characteristics have the same mean stress deceleration in the standard crash test. So first, let's verify the conditions. Try to work it out. Population have approximately normal distribution. And then they do have the same variance. We'll be assuming this example will qualify all the requirements. And then simple random sample and independent samples. And they will be categorized in only one way. Okay, then figure out, we do have 3 population, small, mid-size, and large. How many samples for each population? We do have the 7. Okay, input the data on L1, L2, and L3. Figure out the sample mean and the sample variance. Okay, check your work. And then find out the variance of the sample mean. Plug in these 3 data on your L4. And then find out the sample standard deviation. Take square. You're gonna find the variance of the sample mean. And then the mean of the sample variance. You could add it up, divided by 3. Okay, state the null and alternate hypothesis. We want to test if they do have the equality of the population mean. And we do have a free population. Alternate hypothesis. So at least one of the means is going to be different. Okay, test statistic. Using the formula, N times variance of the sample mean divided by mean of the sample variance. You should get 3.288. Okay, find the p-value and interpret the p-value. So we have the skew to the right, so F distribution. And the test statistic will be here. P-value will be equal to the area of whitetail. Figure out degree of freedom of numerator and degree of freedom of denominator. Try to do it by yourself and use the FCDF, find out the p-value. Okay, check your work. We do have 3 population, right? So K equal to 3. And then they do have the sample size for each population n equal to 7. So you should get degree of freedom of numerator equal to 2, degree of freedom of denominator equal to 18. Okay, p-value. FCDF, lower value, upper value will be 1D99. And then degree of freedom of numerator, degree of freedom of denominator. Use your calculator, you should get this number. And then compare with your significance level. So this is a 0.06, this is a 0.05. So that will be strictly greater than. And fail to reject the null hypothesis. So draw the conclusion. There is not sufficient evidence to conclude that at least one of the car size categories has a different mean chest deceleration in the standard question test. That's it.